The next major leap in green hydrogen won't come from bigger factories or new electrolyzer companies. It will come from something far smaller, quieter, and more foundational. It will come from materials. The world is entering the era of Materials 4.0, where artificial intelligence, additive manufacturing, atomic scale precision, and automated discovery are rewriting how electrolyzer components are designed and built. For the first time, we can point to real companies, real experiments, and real data showing that electrolyzers, which today cost between $1,000 and $2,500 per kilowatt, could fall to as little as $120 to $300 per kilowatt. That is a 4x to 10x reduction. And it is not theoretical. It is already happening in labs and factories across Europe, Asia, and North America. This is the story of how that future becomes real. To understand this transformation, we need to look at electrolyzers the same way a materials scientist does. Not as a machine, but as a collection of expensive components. Catalysts, membranes, flow plates, gas diffusion layers, and stack hardware. Each component has a cost curve shaped by material scarcity, manufacturing processes, and performance limitations. If you redesign the material, you redesign the cost. Materials 4.0 is doing exactly that through three converging forces: digital materials discovery, atomic scale engineering, and advanced manufacturing. Together, they are tearing apart the old cost structure of electrolyzer components piece by piece. And the clearest way to see this is through real examples. Let's begin with flow plates, the structural backbone of hydrogen electrolysis. Traditionally, flow plates are machined from stainless steel or titanium. Machining is slow, costly, and wasteful. A plate that weighs 50 grams may start as a block of metal weighing 10 times as much. The flow channels must be cut, etched, or stamped with micrometer precision. Coatings must be applied. Quality control must be repeated. All of this adds up to plates costing $40 to $80 each. But in Switzerland, a quiet revolution is underway. Exentis Group, a pioneer in high-precision additive screen printing of metals, developed a platform that prints fully formed stainless steel plates with microchannels as thin as 125 micrometers. Instead of machining away 90% of the metal, Exentis prints only what is needed. Their machines can produce more than 1,000 plates per day, not by stamping, but by digitally depositing the metal in exact shapes. The cost implications are extraordinary. A plate that once cost $50 to manufacture can now be printed for under $5. That is not a projection. That is real. Customers already order plates for fuel cells and electrolyzers using this process. The geometries achievable using Exentis' method are far superior to machined parts. Curved channels, fractal flow patterns, micro-lattice reinforcements, and internal structures that were previously impossible now become standard. More efficient flow channels reduce pressure drop, improve gas removal, and increase stack efficiency. In one breakthrough, the company printed plates weighing significantly less than their machined counterparts while outperforming them in fluid distribution. When one component of the electrolyzer drops in cost by 10x and improves performance, the entire cost curve shifts. This is the first pillar of proof. Now, consider catalysts, specifically iridium, the costliest component of a PEM electrolyzer. Iridium is one of the rarest materials on Earth. The global supply is a few tons per year. Prices fluctuate between $150,000 and $200,000 per kilogram. Until recently, PEM electrolyzer anodes required iridium loadings of 2 to 4 milligrams per square centimeter. That made catalysts one of the most expensive parts of the entire stack, and it limited global scaling. But the Materials 4.0 revolution is breaking this bottleneck decisively. At ETH Zürich, researchers created single-atom catalysts where individual metal atoms, iridium, platinum, nickel, or cobalt, are anchored to nitrogen-doped carbon supports. Traditional nanoparticles have only a fraction of their atoms exposed. Most are buried inside and do nothing. Single-atom catalysts solve this. Every atom is active. That means the same catalytic performance with 95 to 99% less iridium. In published results, loadings dropped from 2 milligrams per square centimeter to as low as 0.02 milligrams. That is a 100x reduction. These catalysts are stable, resistant to dissolution, and cheaper by orders of magnitude. What's more, this is not limited to noble metals. Teams at the Korea Institute of Science and Technology have created cobalt-based single-atom catalysts that match or exceed the oxygen evolution performance of iridium. Meanwhile, research from Lawrence Berkeley National Laboratory has demonstrated atomic layer deposition techniques that precisely place catalyst atoms in monolayers, minimizing material usage while boosting stability. These advances reduce catalyst layer costs from over $200 per kilowatt to under $10. Combined with earth-abundant elements, the catalyst bottleneck disappears. The electrolyzer becomes scalable, and catalyst cost drops by 20x to 100x. The strongest single lever for a 10x reduction. Membranes are the next frontier, and they are benefiting from Materials 4.0 just as dramatically. PEM membranes such as Nafion cost anywhere from $700 to $200 per square meter. They perform well, but they degrade under high voltage and high oxygen environments. They require careful casting, fluorinated monomers, and expensive processing conditions. But Materials 4.0 introduces an entirely new paradigm: atomic scale design of ion channels. Researchers at Imperial College London developed nano-engineered membranes with proton-conducting pathways arranged in optimized geometries. They use less fluorination, rely on cheaper polymer backbones, and achieve higher conductivity at lower thickness. Their materials cost between $150 and $250 per square meter, a 5x to 7x reduction. Even more remarkable is the lifetime improvement. Nano-reinforced membranes with engineered sidechains have demonstrated lifetimes of 20,000 to 40,000 hours, double or quadruple the lifetime of traditional membranes. Lifetime matters. If a membrane that previously lasted 8,000 hours now lasts 32,000 hours, the cost per kilogram of hydrogen produced drops dramatically. When combined with reduced material cost, the effective improvement is close to 10x. Membranes, once a cost anchor, are becoming a cost accelerator. Manufacturing itself is the final frontier where Materials 4.0 reshapes the cost curve. And this area provides more real-world evidence. Siemens Energy uses additive manufacturing to produce electrolyzer components with embedded cooling channels and internal pathways that machining could never create. Bosch uses laser powder bed fusion to fabricate complex hydrogen components with up to 85% less metal waste. Fraunhofer ISE has built entire stack hardware structures through 3D printing, demonstrating cost reductions of 70 to 90% for certain parts. One titanium frame that used to cost $900 to machine can now be printed for under $100. These advancements do not just reduce the cost of individual components. They reduce the cost of the entire manufacturing process. When material waste decreases by 80%, when part count drops because designs consolidate multiple components into one printed structure, and when assembly time falls because tolerances become digitally precise, manufacturing cost decreases exponentially. Add to this the fact that 3D printed parts can be produced locally rather than shipped globally, and supply chain resilience increases while logistics costs fall. Combined, these breakthroughs support a 5x to 10x reduction in stack hardware cost. Artificial intelligence is the multiplier that ties all of this together. Traditional materials discovery relied on intuition and testing. It took years to find new combinations. Today, AI models simulate hundreds of thousands of catalyst structures, membrane chemistries, and flow field geometries in hours. Berkeley Lab ran an AI screening program that evaluated 500,000 catalyst candidates in a single day. Toyota's research division used machine learning to reduce precious metal loading in fuel cell catalysts by 95%. And DeepMind's Genome discovered hundreds of thousands of stable new crystal structures, many relevant for hydrogen production. AI shrinks the timeline from discovery to commercialization. What once took decades now takes months. The combined effect of these breakthroughs, 10x cheaper plates, 20x to 100x cheaper catalysts, 5x to 10x cheaper membranes, 5x to 10x cheaper hardware, and 10x faster R&D cycles, creates a new economic reality. Electrolyzers that once cost more than $100 to $200 per kilowatt can fall to $120 to $300 per kilowatt. That is a full order of magnitude shift. When electrolyzers become this cheap, everything changes. Green hydrogen no longer requires policy support to compete. Green steel becomes viable. Renewable ammonia becomes cost competitive. Hydrogen trucking, aviation, and shipping become realistic without subsidies. Entire industries shift, and if these materials can be produced locally through additive manufacturing, regions like Africa, the Middle East, South America, and Southeast Asia can build their own electrolyzer supply chains. Instead of relying on iridium, titanium, or global suppliers, they rely on digital files, powders, and local manufacturing centers. The hydrogen economy becomes distributed, resilient, and equitable. It becomes a digital energy economy where materials are downloadable and electrolyzers are printable. The future electrolyzer will not resemble today's systems. Its catalyst will be single atoms engineered for perfection. Its membranes will be nanostructured highways for proton transport. Its flow plates will be printed with complex geometries that squeeze every bit of efficiency from water splitting. Its hardware will be lighter, stronger, and cheaper. Its manufacturing process will be automated and intelligent. It will cost a fraction of today's price, and it will last twice as long. This is the Materials 4.0 revolution, and it is the clearest, strongest, and most credible path to making electrolyzers 10x cheaper. It is happening now, and it will accelerate the hydrogen economy faster than any policy, subsidy, or factory expansion ever could. To track these breakthroughs and learn how they affect hydrogen project economics, visit h2hub.reneenergy.com. Because the materials of tomorrow will shape the hydrogen systems of tomorrow, and the future of clean energy will be built one atom, one layer, one discovery at a time.